Okay, so now that we kind of understand the purpose of initial conditions and why we use them, I'm going to show you how to use them. So we'll do several examples, and the first one, it comes from our textbook. It's on page 442, example number 6, part A, and it tells us something like our derivative function is equal to 2x minus 3 cubed, and this initial condition is that the original function, so f of 1/2, is equal to 4. And now they want us to find that original function. So our first step in finding the original function is to work backwards from the derivative. And that's a matter of taking an antiderivative. So let's start by setting up an integral. So I'm trying to find our antiderivative, which is going to be something like this. And just to really hit home on this, I'm going to maybe call it big f of x. So really trying to get into our heads that like our big f of x is kind of that antiderivative function. So notice here that I do have some kind of an inner function like this. So if I want to use my u sub technique, it's going to look something like 2x minus 3 is equal to u, and then du dx is equal to 2. But I don't have a 2 in my function that I can directly like substitute in for. So I'm going to pull that 1/2 over here, du dx is equal to 1. Okay, so now let's start by actually substituting these pieces in so I can take an antiderivative. That'll look something like u to the 3rd power times the 1/2 du dx times dx. Those guys cancel, and I'm left with 1/2 u cubed du. Okay, so an antiderivative at this point would say increase the power by 1, divide by the new. So I get 1/2 times increase by 1, I get 4, divide by the new, that's really a 1/4. And so I'm getting this 1/8 times u, which is 2x minus 3, to the 4th power plus c. And technically, sorry, there would be a plus c there as well. Okay, so if I'm taking a look at this here at this point, that plus c is not actually what I want. What I'd like to do is find the actual exact original equation. This is just kind of actually a family of original equations now, where c represents any like real value, real number value. So to find the specific one, I need to use this initial condition, which is technically like a clue about that original function. So the original function, if I were to plug in 1/2 for x, I would get 4 as my y value. I'd get 4 as an output here. So to use my initial condition, I'm going to basically take my candidate function. This is kind of the candidate original function, and then use that initial condition to find out what c is. So I know that if I plug in 1/2 for x, I'm going to get 4 as the output. So I'm going to begin by actually plugging in 1/2 for x. So this is going to be 2 times 1/2 minus 3 to the 4th power plus c is equal to 4. So I took kind of this function, my antiderivative. I plug in something I know about that original equation, and it's equal to 4. And now I can simplify and find out what c is. So this would look like 1/8 times 2 times 1/2 is just 1. 1 minus 3 is -2. And that's to the 4th power plus c equals 4. Okay, so -2 to the 4th power is 16. So this is 1/8 times 16 plus c equals 4. 1/8 of 16, or 16 divided by 8, is just 2. So 2 plus c is equal to 4, and that means c had to have been +2. So subtract that, and I get c is +2. So my actual answer, my exact solution for the antiderivative, is the function 1/8 times 2x minus 3 to the 4th power plus 2. And now that's my exact answer for this antiderivative. I found what the c value was by plugging in a point that I know. If I plug in 1/2, I'm going to get 4. So what was c? C had to have been 2. Okay, so I'll do another example and show you how this works with an e to the x function. Okay, so our next example is also going to come from the book, and it has to do with an e to the x power kind of function, or a natural exponential function. So I wanted to just read the problem so you get an idea of the language. It says that the curve y equals g of x passes through the point 2, 5e to the 8th. The gradient of the curve is given by this function g prime is equal to 8e to the 4x. Find the equation of the curve. So find that original equation. So notice they're talking about gradient functions. Again, that's that idea of a derivative. So we're looking at our g prime here. Now, the first step in finding your original function is always going to be the same. Start with finding an antiderivative or integral. So I'm going to start with our integral of 8e to the 4x dx. And I'm actually going to challenge you a little bit. Rather than going through the whole u sub process, think in terms of this kind of backwards, right? I'm almost going to find my antiderivative by thinking about this as the derivative. So I'm thinking in terms of, okay, well, the e to the 4x is still going to be there. But now if I want to take a derivative back, there'd be kind of a 4 that pops out here. And 4 times what gives me an 8? Well, 4 times 2 gives me an 8. And then plus c. So pause for a second. I know I went through that kind of quickly, but I'm finding the antiderivative by thinking of this as the derivative. So if I look at just this function right now and take its derivative, wouldn't it look something like 2e to the 4x? So the function doesn't really change. And then multiply by the derivative of the power. And 2 times 4 is just 8e to the 4x. And that's what I had here. So I'm kind of just skipping some of that legwork and showing you how to go a little faster through these chain rule backwards, especially when it's just a constant like that you just have to account for. Okay, so this is kind of my family of antiderivatives, where c could be any real number, but now I'm going to think about finding the exact antiderivative here that goes through that single one point. Okay, so 2 is equal to x. And the 5e to the 8th, that's my output, that's my y value. So I know that if I plug into, so if I do, I'm working with g. So if I do like g of 2, that would be equal to 5e to the 8th power. Well, g of 2, I mean, this is kind of my g of x candidate. It's kind of my antiderivative candidate. If I plug in 2 for x, this becomes 2e to the 4 times 2 plus c. And I want that to be equal to 5e to the 8th power. Okay, here I've got 2e to the 8th plus c equals 5e to the 8th. And if I subtract that over here, I'm trying to get c by itself, I have 5e to the 8th power minus 2e to the 8th power. And ultimately, this e to the 8th power, e to the 8th, these are kind of like terms where you can combine them because they both are ultimately that same number. There's 5 of them here and 2 of them there. So when I subtract, I just get 3e to the 8th power like that. Okay, so my final answer for this, the exact solution here for this antiderivative, is going to be the function g of x equals 2e to the 4x power plus 3e to the 8th power, and that's my final exact solution for this problem. Okay, so our last example problem is more of an applications-based problem, and it comes from our textbook. It's the third part of example number 6 on page 442. So I'm going to read this out loud, and I want you to listen carefully to the application problem going on here. So it says, the rate of change of a population of fish in a lake is given by dp dt is equal to 60 square root t for any t between 0 and 4 years. The initial population was 140 fish. Find the number of fish when t is equal to 4 years. So there's a couple of things going on here, but I want to pause and just acknowledge that in calculus, a lot of times we just throw out these these equations and these functions, and we're very mechanical a lot of the times, but we forget that these functions we're using actually model real-world phenomena and real-world situations. So just kind of drawing you back into the fact that this application problem would work using concepts of calculus. So I'm going to write down some of the important information they gave us. Firstly, that dp dt, the change in population with respect to time, so this is like our population function, is equal to 60 square root t, and that works for any t from 0 to 4 years. And they tell us that the initial population in the pond was 140 fish. So that's what we're calling our initial condition, right? It's some kind of initial condition that I know about the function, and in this case, without any time passing, so after 0 years of time passing in the pond or in the lake, there was 140 fish. So when t is equal to 0, there were 140 fish. That's my initial condition. It wasn't super obvious. You had to kind of work for it a little bit, but it's there. Okay, so now I need to find that initial population, because what I want to ultimately do is find out how many fish were there after 4 years. I don't care about the rate of change after 4 years. If I wanted to know the rate of change, bam, there it is. That's my function. Just plug in 4, you're done. But I don't want to know the rate of change at 4 years. I want to know the actual number of fish at 4 years. So I need to find my population function, which is an antiderivative, and then plug in 4 years to that thing. And that's where I need to start with this problem. So I'm going to go ahead and jump right into an integral. Notice the variables I'm going to use here. So this I'm just going to call 60 t to the 1/2 power dt. So your variables that you're integrating with respect to here have to match the variable that's actually in your function here. And by the way, we are finding a population function with respect to time. So it's going to be our p of t function. All right, let's begin with an antiderivative. Let's increase the power by 1. So that becomes 3/2. And then divide by the new, or that's a really matter of multiply by the reciprocal, 2/3. And then plus c, my constant of integration. Or in this case, because I'm really talking about a lot of context here, I'm not going to call it plus c. I'm going to actually call it p naught, or p initial. So it's like a way of saying the number of fish, the population of fish at time 0. So p naught or p0, that's something really common you're going to see in physics and things like that. Okay, so let's go ahead and simplify all this down. And I get something like 60 divided by 3 is 20, times 2 is 40. T to the 3/2 power plus p naught, or initial population. Okay, so the initial condition they give us is that at time 0, there were 140 fish. So that means when time is 0, so p of 0 is equal to 140 fish. And this really becomes a pretty simple problem, because this is just 0 plus 140. And surprise, surprise, that initial population of fish was just 140. So I didn't really need to go through the algebra of solving it, but I wanted to show you that it would work either way. So my population function with respect to time is going to look like 40 t to the 3/2 power plus 140 fish. And now I need to know how many fish were in there after 4 years. Well, that's just a matter of finding p of 4. So I get 40 to the 3/2 power plus 140. When I evaluate this, I'm thinking about the 2 on the bottom is like a square root. So the square root of 4 is 2. And then if I cube that, I get 8. Plus that initial 140. That's 320 plus 140. And that gives me 460 fish. So after 4 years, there were 460 fish in that lake. So initial conditions, right? Any kind of point that's on your original function. If they give you when that point was equal to, or when time or x or whatever is equal to 0, then it becomes pretty simple to actually calculate out. But please confirm it with an algebraic solution, because anytime you have like e to the x powers or something like that, it's not just going to wind up being this pretty. You do need to kind of do the algebra and confirm that the answer is what you think it would be. So there you go.